Hi everyone. In today's lecture, we'll be discussing about the sinusoidal response of parallel and series LC circuits. So what happens when you feed, for example, a sinusoidal current I naught sin omega naught t into u of t to a parallel LC circuit, and similarly the same thing will apply for a series LC circuit. We will be applying a sinusoidal voltage V naught sin omega naught t into u of t. So here I've assumed that the frequency of the sinusoid omega naught matches with the resonant frequency of the LC circuit. We will later analyze a case where the resonant frequency omega, where the input frequency of the sinusoid, is omega x, and that's not equal to omega naught. We'll see what is the difference between the two responses, and we'll try to give an intuitive explanation for the same in this lecture. So first I'll try to mathematically solve if I feed an input I naught sin omega naught t, I naught sin omega naught t for the parallel LC circuit, to the parallel LC circuit, and see what is the voltage that is developed across the tank. So I'll again resort to Laplace transforms to solve the problem. So the Laplace transform of this is I naught omega naught upon s square plus omega naught square, and the parallel LC tank, the Laplace transform can be written as 1 by c s square plus omega naught square, where omega naught here is 1 by root LC, or omega naught square is 1 by LC. So this result I'll write it as I naught omega naught upon c into s by s square plus omega naught square the whole square. Now how do you find the Laplace transform of inverse Laplace transform of this signal, this function? So I'll start with this function, as I'll just use one of the theorems in Laplace transforms, that is, if a signal x of t has a Laplace transform of capital X of s, then if I differentiate x of s, dx of s upon ds with a minus sign, it will have Laplace transform of t into x of t. It's a very simply and a very easily provable result. You can check for yourself. So it will be t into x of t. So what I'll do is I'll take a sinusoid first. So we know sin omega naught t, the Laplace transform of sin omega naught t is omega naught upon s square plus omega naught square. Now I'm going to differentiate this term, so I'd get minus 1 by s square plus omega naught square the whole square into 2s into omega naught. So I'll take minus of x ds of d by ds, that will become plus. So this is like x of t, and this term here is like minus of dx of s by ds. So the Laplace transform is going to be t into sin omega naught t into u of t. So this is the Laplace transform of this function. There is u of t here as well. Okay, so the response here that we got from this equation, so it is I naught omega naught upon c s by s square plus omega naught square the whole square. So I'm going to use this result. I'll just bring 2 to this side. I'll just so if I take 2 on the other side, I just multiplied, if I multiply the signal by half, the Laplace transform also gets multiplied by half. So the inverse Laplace transform of this is going to be I naught omega naught by c. Omega naught would go away. You would be left with I naught by c into t sin omega naught t by 2. So this is nothing but a linearly increasing sinusoid. The sinusoid's amplitude will increase linearly. Eventually, at t equal to infinity, the amplitude, the sinusoid will blow up. You will have an infinite amplitude sine wave. Now, does this result? We'll try to intuitively verify whether this result. Is this result correct or not? So what I'll do is, the instant you apply a sine wave to the parallel LC circuit, I'll try to analyze this result. Find the value of the result for t very close to 0. The moment the input is applied to the system. At that point, sin x can be approximated as s. So this function will reduce to I naught t by 2c into omega naught t. So you would get a result I naught omega naught by c into t square by 2. This is the result you get from this equation. Now if I can show using some simple approximations we'd get the same result at t equal to 0, then that's a good enough a verification for the equation that we have here. So first the input that we are applying is I naught sin omega naught t into u of t. So at t equal to very close to 0, I'll approximate this result to I naught into omega naught t. Now that's the current that's going to fully flow through the capacitor because the inductor will block it. The inductor cannot have sudden changes in the current. So the voltage across the capacitor is integral of 1 by c integral I dt. So integral of the current. So that would be 1 by c. The current is I naught omega naught into integral of t, that you would get t square by 2. So that matches with this result. So again mathematically this result is fine. So that I just wanted to verify that. Okay. So when I feed a sinusoid of frequency which matches the resonant frequency, then the output of this parallel LC circuit will be a linearly growing sine wave. So the sine wave will be linearly growing like this. Okay, so it will be I naught by c into t by 2 sine of omega naught t. So you can if I start from origin, the output sine wave would just increase linearly like this. So we'll find an intuitive explanation for that later. I just wanted to write the mathematical equation for this first. Now in case of this input frequency, now I'll apply a sine wave with an input frequency not equal to omega naught. Let omega x be the input frequency, which is actually not equal to omega naught. In that case, we'll try to find what will be the voltage developed across the parallel LC tank. So again, I'll resort to Laplace transforms here. The Laplace transform of this signal is I naught omega naught by s square plus omega naught square. That is multiplied by the Laplace transform of the system, which is s by c into s square plus omega naught square, where omega naught square is 1 by LC. Now in this result, I naught omega naught by c, I take into s also common outside. I can write this as 1 by s square plus omega naught square minus it's omega x here, omega x square minus s square plus omega naught square. The whole thing I'll just divide the whole thing by 1 by omega naught square minus omega x square. Okay, just a partial fraction expansion of the above result. Now I take s inside the braces, so you would actually get and then if I take the inverse Laplace transform, I'd get I naught omega naught by c into omega naught square minus omega x square into cos omega xt minus cos omega naught t into u of t. Okay, again once I've taken s inside, the inverse Laplace transform for this would reduce to this. Now if I look at this expression, the output sinusoid, I fed an input sinusoid of frequency omega x, but the output sinusoid also contains terms, it also contains a different frequency which is omega naught. Okay, it also contains a frequency which is omega naught. I think there is a small change here. This product here, it's actually omega x. This is omega x and this is omega x. It's not omega naught, it's omega x. Yeah. Now this result, this is nothing but you actually have a sum of two sinusoids, which is the input frequency here omega x, and there is also the resonant frequency that's shown here, which is omega naught. Now this equation, I can reduce this to a form like this, I can write omega x as omega naught plus omega x by 2 minus omega naught minus omega x by 2, and omega naught as omega naught minus omega x plus omega x by 2 plus omega naught minus omega x by 2. So I can write these two terms in this way and reduce this term as I naught omega x by c omega naught square minus omega x square into 2 sine omega naught plus omega x by 2 into sine of omega naught minus omega x by 2. Okay, so again you can see this waveform. It looks like an amplitude. If you know basics of communication theory, this looks like an amplitude modulated signal. Okay, this is like the high frequency carrier. The carrier frequency omega c I'm going to represent as omega c as omega naught plus omega x by 2, and the method signal omega m as omega naught minus omega x by 2. So obviously omega m is going to be less than omega c in magnitude. So if mod of omega m, I mean here again omega m is the magnitude of this. This will always be positive, but this can be negative depending on omega x being greater or less than omega naught. So here I am going to get a result like this. So you can visualize this as some kind of an amplitude modulated wave with a carrier frequency given by omega naught plus omega x by 2 and message signal by omega naught minus omega x by 2. Okay, so when you take it for a transform and see, you essentially you will actually contain two tones. There will be a tone at omega x and there will also be a tone at omega naught as well. So that's what I'm trying to explain using this. That's what we actually obtain when we directly derive the equation for the sinusoidal response. Okay, so we'll try and see. Now if you look at this output, cos omega naught t minus the input, that is the, when I look at the expression for the output here, this term doesn't blow up. It's always finite. The amplitude of the signal, even though it exists for for all time, it's never going to blow up, right? In the previous example, when you fed an input of frequency omega naught, the output was actually giving an infinite output when t tends to infinity. On the other hand, for this, when you feed an input of a different frequency than the resonant frequency, the output will never blow up, but it also contains two different frequencies. It also contains another frequency, omega naught in this. Okay, and again that should sound intuitive, because I said in a resonant system, if I feed any sinusoid whose frequency matches with the resonant frequency of the system, the amplitude of the output sinusoid is obviously going to be much greater than the input. And since this is a lossless resonant system with an infinite gain at the resonant frequency, you should actually get an infinite gain, the steady state, and that's what happens in the first case. We got an output I naught by 2c t into sine omega naught t into u of t. So that's the output we got. The output was linearly increasing as a function of time. Okay, so this is a resonant system with an infinite gain at the resonant frequency f naught. F naught is 2 pi omega naught by 2 pi. Okay, and we fed a different frequency. When you fed a different frequency to this system, you are getting a bounded output given by the result that is shown here, which is this. I've reduced it into sinusoids, using sum and difference frequencies, but essentially what you get is actually two frequencies at the output. Now I'll try to give an intuition why should that happen. So when you feed a sinusoid to a resonant system, I'll just take an LC circuit, parallel LC circuit. So if you are feeding a sinusoid, this is a current now, it's a sinusoidal current, and I naught sine omega naught t into u of t. Okay, so the input so in this half cycle its input is positive, in the other half cycle it is negative. So to understand this, what I'll do is I'll just try to analyze the problem by using impulses. Okay, it's easier to analyze it using impulses. So I'll assume that there is an impulse. I'm going to consider the area under this sine wave and then lump it together as an impulse at t equal to 0. Okay, and in fact I can do it at the it doesn't matter when I introduce the impulse. So I can lump all the energy, all the area under this graph. Since it's a current, I can call it as a charge and then lump it together as an impulse at t equal to t by 4, the center of this curve. Okay, and similarly this area, I can assume that you are transferring a negative charge to the circuit, to the system. Okay, and I'm going to show it again by an impulse. So you should understand these two impulses are located at the center of this sine wave. So the spacing between the two centers will be t by 2. Okay, so this will be t by 2. So I'm going to assume q is the charge here and minus q is the charge here, where q here is nothing but the area under this integral. You can find that value of the integral. Okay, so I'm assuming q is the charge that's being transferred to this circuit. So you can easily find, that area under the sine wave. So I naught sine omega naught t integrated from 0 to t by 2 dt. So you'll be left with I naught by omega naught into cos omega naught t 0 till t by 2. When you substitute, so there is a minus cos, and when you integrate sine you get minus. So you would actually get I naught by omega naught into 2. Okay, so if you substitute omega naught as 2 pi by t, so you would actually get I naught by pi, I naught t by pi. So that will be the total charge that is transferred in 1/2 cycle to the tank, to the LC circuit. Okay, so this q here, well, actually is I naught t by pi. I am just using that. It really, the value doesn't matter. I'm just trying to illustrate an idea here. So what happens at q, the instant I'm going to inject this charge. So here I'm going to inject this charge at t by 4 seconds to a parallel LC tank. So what is going to happen is that the instant the LC tank sees an impulse of charge, we already know that the inductor will offer an infinite impedance, so it will instantly flow through the capacitor. Now since it's an impulse of charge, the charge transfer is taking place instantaneously. Okay, and so there will be a step voltage across the capacitor. So when the capacitor sees at t equal to t by 4 a sudden change in the voltage, okay, so the voltage across the capacitor will be q upon c. So there will be a sudden jump in the voltage here, which will be q by c. Now we already saw it in one of the previous lectures. So when you feed an impulse of charge, so when the voltage suddenly jumps up, the inductor will now start discharging it. Now by the time it reaches 1/2 cycle, so this is actually 1/2 cycle, it would start discharging it. It would come to this point. The voltage across the capacitor would have become negative minus q by c. Right? So in 1/4 of a cycle, we saw that the capacitor voltage will be discharged by the inductor and the energy will be fully stored in the capacitor and inductor as current. Then the current will further charge the capacitor in the negative direction and it will take the voltage to minus q by c. But at minus q by c, we are again injecting a charge of minus q. So it's going to add up to the capacitive charge in negative, because the capacitor voltage is negative and you are feeding a negative charge, so it's going to increase the capacitor voltage. So suddenly there will be a jump in the capacitor voltage. Okay, so this is going to continue forever. I didn't show that. Every t by 2 seconds you are going to get an impulse. You are going to get the sign of the impulses will keep alternating. So now the instant this charge is increased, now what would happen is that in the next half cycle, again the same process would continue. The frequency will remain the same, but the initial charge is different. So you are actually going to have a waveform like this. in the next half cycle with an increased amplitude, with the amplitude will be twice. So by the end of one cycle, this is 0 t by 2 t, the amplitude of the sine wave is twice than what it began at t equal to 0. Now again at t equal to t, you are injecting a positive charge. So the capacitor is going to store that charge. Okay. So now if you see this impulses, by injecting impulses every t by 2 seconds, what I am doing to the system is that I am actually increasing the charge delivered to the system. I'm every half cycle I am adding more and more energy to the system. The energy is always adding constructively. So since I'm adding energy to the system and there is no loss in the system, so it's going to store it. So at t equal to infinity, since it is always going to store the energy, eventually the amplitude would blow up to infinity. So that's what is actually happening when you feed a sine wave. In the positive half cycle, you are transferring energy to the system. Even in the negative half cycle also, you will be transferring energy to the system. Okay, and that we showed it using an impulse, negative impulse, how we are actually transferring charge. Okay, again you can very easily show that since at the moment the current is being transferred, the voltage is positive here, the voltage across the tank is positive, and you are injecting current into the tank. So you are actually, the current source is actually delivering power. So same way, when the voltage across the tank is negative, you are injecting a negative current into the tank. So again you can say that the power is being delivered to the tank from the current source. So the current source is always delivering power. Okay, we saw in one of the previous lectures that sometimes the current source also dissipated power, but in this case it's always delivering. So that's what happens when you feed an input of frequency omega naught. Your input will always be in the power delivery mode. It will always be delivering power to the LC circuit. It will never dissipate power. That's all I'm trying to say here. Okay, so and since that energy is always stored, it's always stored in the inductor again and again, so your amplitude will eventually blow up to infinity. Okay, so that's what happens here. I mean, I've just left this problem here. So at t equal to t, again the amplitude will increase further. Okay, so it will further increase, and again when t equal to minus t, it will have a further increase in the amplitude, and so on. So it will be an ever increasing amplitude sine wave. So that's what we saw when you fed an sinusoid, and here you can also see it increases linearly. Okay, so that's one way of explaining this. Now to explain the other case where the sinusoidal frequency is not same as the resonant frequency. To explain that, I'll consider a case where the frequency is a subharmonic, meaning you are going to inject a positive charge at 0 and you are going to inject a negative charge at t equal to t, and then we are going to inject a positive charge at 2t and negative charge at 3t. Now if you look at this signal, if you actually find the Fourier transform of this signal, it will not contain any harmonics. So in fact the fundamental frequency of this is 1 by 2t, because at every 2t seconds it's repeating itself, and since the signal is actually odd symmetric, that's again a properties of Fourier transform, you will actually not have any even harmonics in the signal. So you will only have 2k plus 1. So since 1 by t, I will call it as f naught. So 2k plus 1 by 2 into f naught. So that will be your frequencies which are present in the output signal. So now if you see the resonant frequency is f naught, since this can never be even, okay, you will never have energies at f naught or even multiples of f naught. We only care about f naught. Since k is an odd number, I mean this 2k plus 1 is an odd number, you will never have tone at f naught. So what we'll see what happens when you feed this input to the resonant system. So in the instant you give an impulse, suddenly there will be a voltage developed across the capacitor of value q upon c, and then till t 0 to t, it's going to undergo one full cycle. There will be transfer of energy from the capacitor to the inductor, and capacitor gets it back at t equal to t. But at t equal to t, what you are doing here is that you are injecting a negative charge of value minus q, this voltage is q by c. So the voltage across the capacitor will instantly go to 0 at t equal to t, and then it will stay there, because you have suddenly made the energy to go to 0 at t equal to t. Now what happened here is that the current source, if you see, was negative here. The current source is actually transferring a negative charge, but the voltage across the tank is positive. So therefore the power will be dissipated by the current source. I mean, where is this energy? There was an energy which was stored across the capacitor. All that energy is lost instantly, and that is lost across the current source. The current source dissipates this energy and it brings it to 0. Now again, this is at t, 0 to t, and at 2t again you are going to give some energy into the system, and it will oscillate till 3t. Capacitor will get the voltage back at 3t. Again at 3t you are going to inject a negative impulse, and the voltage will suddenly come to 0. So now if you look at it, because the current source is sometimes delivering energy, sometimes it is absorbing energy or taking energy away from the tank, the output will never grow unbounded. It will always remain finite. Okay, so what happens essentially is that when you don't give a frequency matching with the resonant frequency, sometimes you will be transferring charge, and sometimes you will actually be removing charge, or sometimes you will be transferring energy into the tank, and sometimes you will be removing energy from the tank. So therefore the output will never grow unbounded. So when you feed a frequency which is exactly equal to the resonant frequency, you will always be adding energy to the tank, both in the positive and negative half cycles. So therefore the tank will keep on storing the energy. Okay, and since it's a sinusoid, it's everlasting, it will exist for all time. You will be transferring energy continuously. Eventually the energy in the tank will also blow up to infinity. So the amplitude of the sine wave is also going to blow up to infinity. Okay, so this is one intuitive way of explaining it. So that's about in this lecture I mainly wanted to discuss about sinusoidal response to LC circuits, tank circuits. So we saw that when you actually feed a sinusoid of frequency which matches with the resonant frequency, then the output was linearly growing. It was a linearly growing sinusoid. Eventually the amplitude became infinity. Okay, and the stored energy in the tank also becomes infinity. And we saw that if I give a frequency which is slightly different from the resonant frequency, then the energy will not, the amplitude energy stored in the tank will never blow up to infinity. Okay, and we showed it using an impulses example here. That's because sometimes you transfer energy and sometimes you absorb energy from the tank. Okay, if your the frequency of the input doesn't match with the resonant frequency, you will also absorb energy from the tank. So therefore the output will never blow up to infinity. Okay, again I've just derived it for a condition when it is f0 by 2, just to show it's easier to graphically show it. You can use it for, think logically, intuitively for any other frequency, because it's not exactly going to repeat itself. You will remove, sometimes you will be adding energy and sometimes you will be removing energy from the tank. So that is one way to intuitively see the amplitude will never blow up to infinity. So in the next lecture I'll try to give a frequency domain interpretation of all the results so far we have discussed, the step, impulse and the sinusoidal response of parallel and series LC tanks. Okay, I have not discussed the series LC circuit, but it should be pretty obvious. The transfer function is same for both of them. Okay, there is only 1 by L. The difference is the same way. When I apply sinusoidal voltage input to the circuit, the current developed in the circuit will be a linearly increasing ramp. So once you know the current, you can find the voltage across the inductor by using L di by dt. And once you know the voltage across the inductor, you can also find the voltage across the capacitor. And all the voltages across the capacitor and inductor will all be increasing linearly with time. Okay, the tank energy itself will increase linearly with time. So both the inductor current and the capacitor voltage will also increase linearly with time. Okay, so I'm not writing exact equations for it, but once you know, I've derived the equation how to find the voltage across a parallel tank. From that I can also compute for a parallel tank I computed the voltage across the tank. So from that we can easily compute the currents through the inductor and capacitor. Okay, so everything in this circuit is known. Similarly, for a series LC circuit, I can easily compute by a similar procedure. I can easily compute the current flowing in the tank, and once I know the current, I can find the voltage across the inductor, and once I know the voltage across the inductor, input voltage minus the inductor voltage will be your capacitor voltage. Okay, that will be Vi minus VL. So from this I can also find the voltage across the capacitor. And all I am saying is that if your frequency matches the resonant frequency, all these quantities will be increasing linearly with time. Okay, so that's it for today's lecture. In the next lecture I will discuss about an intuitive response from frequency domain for all the responses so far we have discussed for parallel and series LC circuits.